the switch is being rising in. So that's how you combine the two different level sensitive latches to form an edge sensitive flip-flop. Okay, an edge sensitive flip-flop. Now, by now, you probably understand digital designer. The key thing is, how can we keep improving the circuit? So we look at this guy. Okay, how many transistors is needed? We need 8 for this one, 8 for this one, so total 16. 16. Much less than whatever required previously, which is 26. But still, can we do better? That is one thing that you want to ask yourself. Secondly, for this flip-flop, you see that your clock is going to drive all these transmission gates. So your clock is going to be heavily loaded because you need to drive 4 transmission gate switches. So even the transistor required is smaller, but since I need to drive so many clock devices, so they could actually present a heavy loading into the clock driver. So can we do better? And therefore, people come up with this design. Since you want memory element for the latch, there is actually no need for you to put the switch in between. There is no need for you to put the switch in between. This is the memory element. So as long as you are able to drive the key and change this memory contain, then everything can change. And then when you activate this switch, if this is able to drive this element contain and change the element, the memory element contain, then everything can be done without the additional switch. Compare this guy with this guy. Okay? The good thing of having this switch is that you make sure the memory element would not become memory element when you activate this switch. You get the point? Okay. When you open this switch, when you close this switch, you are opening this switch. Alright? So when you close this switch, your input is going to change these 3 inputs. But when you open this switch, it means you no longer have the back-to-back connected inverter. So you no longer have element, memory element. Because to form a memory element, you always have this kind of structure. That is how you form the memory element. Because when you have 0 here, you have 1 here. 1 here will reinforce this guy to be 0. 0 will reinforce this guy to be 1. So that is how you form the memory element. Okay? Or similarly, if you have 1 here, okay, and 0 here, 1 will reinforce output to be 0, 0 will reinforce this guy to be 1. So again, you can retain the value. So the memory characteristic appear because of these 2 inverter connected back. Now, once you break the connection, so when you change this guy 1, this guy 0, this guy 1, there is no reinforcement because this guy and this guy, they are not connected. And once this input disappear, all the value disappear. You get the point? Because this is not memory anymore. So having this switch, the main function of this switch is that you open it, it makes it very easy for you to change the content. And then when you close this switch, you retain the memory characteristic again. So, but in this case, when you try to close this switch, you try to write the data D input into this memory element. You didn't break the loop of the 2 inverter connected back to back. So whether you can write or not depend on whether your writing is strong enough. So as an example, supposedly, originally this is stored as 0, this is stored as 1. Now you open this switch, you close this switch, you want to write a 1 into the memory element. You need to make sure that this 1 is strong enough to override this 0. If you look at this inverter, let me draw out this inverter, it looks something like this. So this is 1. So the PMOS is actually open circuit. Because this is 1, the NMOS is actually short circuit. So it's actually keep pulling down this state to 0. Because you are activating this guy to 1. Now here, if you want to drive this guy, you are actually having a transistor connected to here, and you want to enforce this VDD and change this guy into VDD. So so that you can change the content from 0 to 1. Following me? But this transistor is trying to pull it down to 0. So you're actually having two transistors fight each other. Am I right?
Wouldn't that be like a short circuit?
Yes, it will be short circuit. This guy is also short circuit. So now what is this voltage? If this guy is stronger, then this will leaning toward VDD. You can view these two as two resistors, right? I can view this guy as two resistors. There is one resistor here, so VDD here, and then this is another resistor, and this is the guy originally 0, but once you have the resistor here, if this resistor is very small, then this voltage here will tend to be VDD. Now, if the resistor here is smaller, then this voltage here will tend to be 0. So basically, it's two transistors fighting each other. So in this design, you have the problem. You have to design carefully. The previous design, it doesn't matter because you don't have anything fighting. When you are writing, you don't have anything to fight this input writing. So you can design the transistor easily. You don't care about the sizing. But here, by removing the switch, the good thing is now you see my clock only has to drive through two transmission here, so it's almost half the load. Not only that, each latch is only 6 transistors, so the different floor only requires 12 transistors. It's a lot, about 4 transistors less compared to the original one. But in return, there's a trade-off. By doing that, removing the intermediate switch, now you face this situation when this memory originally retained 0. Now you want to override it to be VDD. You have this transistor fighting with this transistor. And you want to make sure that this transistor wins. If this transistor doesn't win, then you can never override the content. So this memory remains to be 0. You get the point? Okay? So it means you have to select these two transistor sizing carefully. Make sure that this is much larger compared to this guy. This is much weaker. So that during the fighting, this guy will always win. Because when this guy is large, the resistor becomes very small, so this voltage will tend towards VDD, and then you can override.
Wouldn't there be a lot of current?
Come again?
Wouldn't there be a lot of current through it?
Yes, I'm going to bring up that.
That makes heat.
I'm going to bring up that because remember I asked you two main issues for this circuit.
Okay.
So one of the key issues is that the design is not straightforward. Unlike the other guy, you can select any sizing, usually it works. But for this guy, you save the number of transistors, but when you design it, you have to be careful. You have to make sure this guy, the sizing for this guy is much larger than this guy, so that you can override the content. Okay? Similarly here, you need to make sure that this guy is 1, right? So now you want to override guy, this is 0, so you have the same issue. Here, you are going to have a PMOS, which is 1, VDD, okay? And then connect to a switch. That's considered as a switch. But this guy originally is 0, so you are going to add an NMOS pulling it down. So similarly, you have these two transistors fighting. This guy is from here, this guy is from here. So you have to design carefully. Make sure that these two present much smaller register compared to this guy, so that I will be able to override whatever the content store over here. Okay? So in this design, usually one thing you need to do is these two inverter is not symmetric. Same thing, these two inverter is not symmetric. This guy usually is much larger compared to this guy. Because you want to make sure that this guy can override this. Okay? And this one doesn't fight with the other. So that is one issue. It complicates the design. Second issue is like what you mentioned. Now, what is the problem when this guy is on and this guy is on? A lot of current. Because when this guy is on, you directly have a path that short the VDD to ground. You get the point? Because this transistor is on, this transistor is on. You basically have a direct current path connected from VDD all the way to ground. So there is a huge amount of current shoot up. Okay, of course you can stop it after you override it and then you off the switch. But it depends on the clock. If you write it for the full half cycle, if it's during this full half cycle, there will be a huge current going through. Okay? And that consumes a lot of current. That consumes a lot of current. So that is the two key issues associated with this kind of D-flip-flop design. In return, you save the area, you reduce the clock buffer. Okay, so trade-off. By now, as a fourth-year student, you are going to graduate student, you know engineering is always about trade-off. Trade-off. You gain something, you lose something. If people telling you there is one thing that you always win, behold, okay, you might get cheated. Okay. Now, of course, we are not happy with just simple D-flip-flop. Sometimes we want to be able to set or reset the content in the D-flip-flop. So to do that, it's a simple thing by simply putting a name gate. Okay, replace one of the inverter with name gate, then you can reset the content. Okay, if you want it to be setting, then probably you change the name gate. Change the name gate here. So you can have set, reset, or both of them. Okay, you can either have set, reset, or you can have both set and reset for the D-flip-flop. Now, for D-flip-flop, one of the concerns is actually the so-called hold time and setup time. Basically, it means that if you want the content D to be written to the output Q, you better make sure that the content D arrive before certain time. And it better don't change after the clock edges for certain time. So this is the so-called setup time, this is the so-called hold time. Only when the input D is valid before the setup time and valid after the hold time, then your result will be written to the D-flip-flop output correctly. Now, if you violate this, for example, here, I purposely narrow the setup and hold time. What is going to happen is that when D goes to the low, the Q prime try to follow. But before it can fully go down to 0, and therefore activate the changes, your clock is already, your data is already, your clock is already going in, so your input Q prime didn't have sufficient time to go all the way to the 0, and therefore your Q would never have the chance to change. Okay, so that's why setup and hold time is very important in the D-flip-flop design. And all the digital software, the synthesis tool, what they do is they automatically calculate and make sure that the path delay will have sufficient slack, so that in the digital synthesis you usually set out the clock period, and then they will calculate. Let's say I go through the combinational logic, how much delay is going to take, and after go through that delay, will it overshoot the period needed before the next rising? If you overshoot, in this case, it's a problem. It's a timing path violation issue. Otherwise, the design should be working. There is even more compact design. Look at this one. Just now we already have one. For this design, we already have eight. Sorry, not this one. 1, 2, 3, 4. Consider this to be inverter. So you have 8 here, 8 here. So that is about 16, or if you remove the switch, that would be remove 4, that would be 12 transistors. But if you use the dynamic flip-flop logic, you only require 8 transistors. So there is almost 50% saving in the number of transistors. So again, dynamic logic family. So you have already learned a few logic family. Static CMOS. This is the most popular. Transmission gate, simpler, and there's another one called dynamic logic. Okay, so you already learned 3 logic family. Now, usually for synthesis, people use static CMOS because it's very standard. You don't have to worry about it. Sometimes they also have the D-flip-flop implemented using the transmission gate. But for digital cell synthesis, usually you don't see dynamic logic. So dynamic logic is being used when you want to customize the digital design, make it to be high speed, low power. People usually will look at dynamic logic. A very simple example here, you can create 8 transistor D-flip-flop using dynamic logic. Very easy. Before we do that, let's look at one inverter. this inverter, what did they do? What did they do? So basically, you have the input D coming in. Now, when you activate the switch by sending CK bar high and CK low, so basically the switch is being activated, short circuit. Then basically this guy just behaves like an inverter, am I right? Because you can consider this guy short circuit, short circuit. So this is nothing but just one inverter. Agreed? Okay. If this is just an inverter, it means the D will result in the output being, let's say D is high, it will result in the output being low. If D is low, it will result in output being high. So basically this just behaves like an inverter and you can override whatever the content is with. Okay? At that moment of time, this CK is low, so CK bar becomes high. CK is low, so this guy doesn't turn on. So this two switch doesn't turn on. And therefore this guy is not affected. It's not affected because it's like open circuit. You only have a capacitor here. So it doesn't affect anything. Now then, at the moment, when you try to change the CK from low to high. So when you change the CK from low to high, this PMOS now open circuit. CK change to high, so CK bar becomes low, so NMOS also open circuit. So therefore, this node is isolated from the input. But at the same moment, since this node is isolated from the input, but whatever the previous input, let's say this is low, so this guy becomes high. So now, this part gets activated, so the switch is short circuit, and now whatever this guy behaves like inverter, and if this is high, it will drive the output low. If this is low, it will drive the output high. Get the point? So that is the operation principle. And it's a difficult because if the input D is low, you end up having two inverter, output is low. If input is high, after two inverter, output is high. Okay, so it's a difficult. Now, the problem with this circuit is that there is one state, we call it, actually this, we have a nice name for this. This inverter, we call it tri-state inverter. Tri-state inverter. Now, inverter, you know they have two states, am I right? Low or high. Tri-state means we have three states. So what are the third state? What are the third state? The third state happens when these switches are open. When these switches are open, this is what we call high impedance state. High impedance state. So for this inverter, they actually have three states: low, high, and high impedance. We usually call it Z. High impedance, three states. So this dynamic logic basically rely on the capacitor to store the intermediate value. Store the intermediate value. So when the input coming in, the result is being stored in the capacitor. So have you heard of DRAM? Now SRAM is basically, it doesn't change the content as long as the supply is there. But DRAM is basically using capacitor to store. It's very simple. If you have charge, it means 1. If you don't have charge, it means 0. Right? What is the problem with capacitor? What is the problem with capacitor storing the charge?
No power loss.
The inverter bistable also no power loss. What is the problem with DRAM? DRAM is very simple. The DRAM, basically they just have a capacitor and they just have one transistor switch. That's why DRAM is so high density, very compact design. And you know how to make the capacitor? They don't do this because this is very occupying area. So what do? They do something like this. So they go deep, vertically. So when you look from the top, occupy a very small area. So it's like, instead of building the terrace house, you build flat, right? High-rise building. So for the same area, you can put a lot more population. So same concept. But what is the problem of using capacitor as memory?
Storage. Can't store very long.
Can't store very long, storage long, because there is always leakage. there is always decay. So that's why in DRAM, I don't know whether you are aware, DRAM requires constant refreshing. Constant refreshing. So the way the DRAM works is that if you access the memory, it automatically gets refreshed. If you write the memory, it also gets refreshed. But if the memory didn't get accessed for a certain time, then the computer actually have to constantly read and write back again so that it gets refreshed. Okay, it gets refreshed again. Otherwise, after a while, the capacitor just decay. So this is all coming from this equation. I equals to C dV dt. Okay, how long it can store? How long it can store depends on the leakage current and the capacitor value. If you have large capacitor, it can store very long, right? But here, although I show the capacitor, to be frank, we don't intentionally put the capacitor there. So this capacitor is inherent in this transistor. So you don't have to put any capacitor. In fact, over here, you also have the diode. So also have capacitor. So the capacitor for this guy is parasitic capacitor. So you don't expect it to be very large. Okay, it's parasitic. You don't expect it to be very large. So this capacitor is not very large. Then the only thing you can rely on is the leakage current. When does the leakage current? If you think carefully, this guy actually has diode. This guy actually has diode. Diode, you have already learned in 2027. When the diode is reverse bias, is the current really zero? How small is the current? Nanoampere rate. Nanoampere rate. So, nanoampere rate. And you can do a calculation. Let's say this is VDD. Okay, the capacitor usually is very small, maybe femtofarad. Okay, divided by nanoampere. How long can you retain the memory? Okay, the VDD is 1 volt, for example, nowadays. 1 volt. So do a calculation. 10 to the power minus 15, 10 to the power minus 9, multiply by 1 volt. How long can it last? How long can it last? Microsecond. So after microsecond, everything dies. And you cannot wait until microsecond. Microsecond means the capacitor discharge all the way from VDD to ground. So basically, when you discharge to half VDD, you already lose the information. So which means you can only retain by 500 nanoseconds. 500 nanoseconds. So what is the problem with this guy? Your clock speed has to be at least, if the data disappear within 500 nanoseconds. So your clock speed better be faster than 500 nanoseconds, which means 2 megahertz, not gigahertz, 2 megahertz.
Would you just get a bigger capacitor?
Come again?
Would you just get a bigger capacitor and then you can make your clock?
But then you
take more space.
That's right. And also you consume. That's right. So for digital design, we always want it to run faster and we want the error to be small. The reason we choose dynamic logic is mainly because it only requires 8 transistors. Now, if you still use 8 transistors, but each transistor is double the sizing, then equivalently you're using 16 transistors, am I right? Then it defeats the whole purpose. So dynamic logic, that's why dynamic logic is usually used for very high frequency operation. Anyway, you know that for that kind of operation frequency, the charge is not going to disappear. So therefore, I can comfortably use it without oversizing things. Okay? So dynamic logic is very suitable for high-speed operation. But remember this, they have a minimum operating clock. If you operate dynamic logic below the clock frequency, it won't work because everything disappears. Okay? So there is the good thing and bad thing about dynamic logic. Okay, once you have the flip-flop, what can you do? You can use this flip-flop to construct some circuit. Yes? Clock divider. We can use it to do some simple thing. For example, clock divider. To get the clock divider, you basically connect the Q bar output back to the input. Very simple, just different song. Connect the Q bar output back to the input. The logic is very simple. When your Q bar is low, your Q is high, so it connects back to the input. D is low. Once your edge trigger, the positive rising edge trigger, the low will go into the Q. So now Q becomes 1. When Q becomes 1, Q bar becomes low. Okay? So that low go back again. Okay? So now the next rising edge, this low will get transferred to Q. So Q becomes low again. Okay? And then Q bar becomes high. So the whole process just get repeated. So you can see that when the input is like this, okay, but if you look at the FR, so originally it will stay high for one cycle. During the next rising edge, because of the Q bar, the data becomes low, and then the data during the next rising edge becomes high again. So effectively, you are dividing the frequency by 2. Okay? Now if you want to divide by 4, what do? Cascade. Right? Cascade another one. Divide by. This is very good if you want to divide by multiple of 2. Okay? You can keep doing that. You can keep doing that. Now, so this is the typical example to show you how to create a counter, a 4-bit counter. So this is exactly what we do. The clock coming in, and then this guy get divided by 2 times, get divided by another 2, another 2, and another 2. So effectively, you are designing the clock. You are dividing the clock by 16 times. Because 2, 4, 8, 16. Okay, you are dividing the clock by 16 times. So you are effectively having a 16-bit counter. 16-bit counter. So if you run the clock like this, you notice that the Q0 will go like this. Okay? And then the Q1 will go like this. Okay? Every rising edge, because I'm using the Q bar to drive the CK, so only the falling edge, this will happen. Okay? And then you're using this kind of drive, so only during the falling edge, this will happen. Okay, so on and so forth. And if you count, basically you see this guy as 0, 0, 1, 0, 1, 0, 0, 1, 1. So this is the most significant bit. The next one, the least significant bit. So if you look in this manner, you see this actually counting from 0, 0, 0, go to 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and you reach 1, 1, 1. Once you reach 1, 1, 1, what happens? 0, 1, 1, 1, you get reset. So all the counters go back to 0, 0, 0. Okay? So previous slide, we show you a 4-bit counter, and we show you using this NAND gate, how do we reset. We also show you how you arrange this guy so that you will not suffer from the critical path issue, basically by putting the most latest signal to the higher connection. So put it to the NAND gate that is higher connection. But in this example, we're going to show you how can we design an even better circuit to make it even faster. Okay, to make it even faster. Now you notice that, as mentioned previously, all these signals already settled. For example, this guy is 1, this guy is 1. So we are only waiting for the last signal, Q0, to come in, so that you can generate the NAND gate reset signal and reset every counter. Right? So actually everything depends on this Q0. The other signal is already settled. So in that case, I really don't have to use a 4-input NAND gate. Because the problem in 4-input NAND gate is that although this 3 signal is already there, I still have to wait for the last one. So if I wait for the last one, basically it will go through one NAND gate, another NAND gate, before it resets. So you actually have to go through 2 gate delay. 2 gate delay. So how can we simplify this? We can split the 4-input NAND gate into a 3-input NAND gate followed by an OR gate. So how do we do this? So 0, 1, So when Q0 is 1, you want to reset, right? If you want to reset, it has to be 0. So there must be some issue here. If this is 0, 1, so basically it's 1, 1, 1, 1, this is 0, 1, 1, 1, this guy becomes 0. When this is 0, you reset everything, right? So when this guy is 1, 1, this becomes 0, so this guy has to be Q0 bar. Q0 bar. Okay, not Q0. Q0 bar here. Now, how does this help us? If you look carefully, this NAND gate, although it seems like it depends on this guy, but the signal has been settled long ago, because Q3 already settled long time ago, Q2 already settled long time ago, Q1 already settled long time ago, which means this signal already settled long time ago. Then look at this signal. So everything depends on this guy. When everything depends on this guy, it seems like I didn't improve anything because this guy still go through 1 gate and then 2 gate. But is it really the case? If you look carefully, this is OAI, right? OAI. OAI is actually not 2 gate. It's actually 1 single gate. Because you can design OAI using this thing, right? OAI. It seems like 2 logic gate, but actually it's not, because you can combine OR followed by AND and then invert. So everything is formulated using 1 single gate. So by doing that, you actually cut the delay down by 1 gate. Not only that, for 4 input NAND gate, no matter how good your design is, you have 4 transistors in series. Agree? Yes or no? 4 input NAND gate, you have 4 transistors in series. When you have 4 transistors in series, you learn about the equivalent sizing. The equivalent sizing is going to be reduced by 1/4. So it's going to become weaker. Okay? So no matter how good you are, unless you are willing to size each transistor very large, otherwise the equivalent sizing is going to be reduced by 4 times. So it's going to be slow. Okay? And by splitting this guy into 3 input NAND gate and into here, this guy, the design, basically you have 2 transistors in series. So the time can be speed up much faster. Okay? So with this simple counter example, this is actually very simple counter example. We illustrate to you what digital engineer do to make the design faster. Okay? They basically have to examine everything and see what are the things that we can squeeze further. Now, if you don't think about it, just the usual way of designing, it also work. It also work. If you do something like this, it will work, no problem. Okay? But if you do like this, you could get the circuit to run at higher clock frequency. So that's why, in the old day, why Intel processor can run at a few gig, and then AMD either overheated or either at the lower speed. Okay, so the digital engineer between this company does make it. Okay, let's move on. ALU unit. Now this is actually the key block in the CPU. Okay, in the CPU, ALU unit. Basically, it means arithmetic logic unit, and you can make it programmable. Okay. So what does this ALU do? By using this ALU, you can make this guy to perform either exclusive OR gate. Like I said, ALU, arithmetic logic unit. So this guy is actually programmable. It's like a multiplexer. So if depending on which input you are selecting, if you are selecting this input, then you actually have yourself an exclusive OR logic. If you select this input, then you basically get yourself an OR logic. You select this guy, you get yourself AND logic. So you make it programmable. So depending on what you do, you can select different logic. But there is one thing, arithmetic, meaning that you also can perform addition. So we already showed to you how to create exclusive OR gate and AND gate. So now let's take a look. How can we create the adder? Once you have all these things in picture, you can create yourself ALU unit, which is heavily used in computer. Okay, so let's look at full adder. Let's look at the full adder. Now, binary adder, you already know, right? If you look at the truth table, A, B, and then for adder, you have the sum and also the carry. So if it's 0, 0, then both sum and carry is 0. If this is 0, 1, sum becomes 1, carry is still 0. 1, 0, sum is 1, carry is 0. 1, 1, sum is 0, but carry becomes 1. Right? So that is the full adder logic table. Full adder. Now, half adder, usually they don't have the carry. Okay, for half adder, they don't have the carry. So it's carry operator. There should be a C in also. 0, 0, and then you have also 1, 1, 1, something. So, full adder, basically including this guy. Okay, include these 3 input and these 3 output. Half adder don't have this guy, don't have this additional input carry. Okay, they only have this A. Output is always C and C out. So for the sum, it's very easy. For the sum, this is full adder. So for the sum, you just basically using exclusive OR to check the 3 input A, B, and carry in. Okay, as long as the odd number of 1 for these 3 input, then the sum has to be 1. Okay, so the logic for this guy is very easy, understandable. And then for carry out, as long as you have at least 2, 1 for these 3 input, then the carry should be 1. So therefore, you can either have AB1 or ACI1 or BCI1. So again, very easily understandable, okay, for the logic. Now, this is the usual way to represent the full adder. You can also represent this guy by rewriting the function. For example, you create another 2 variable. You call this guy generate and this guy propagate. For this generate, you basically just A and B. For this propagate, you basically A exclusive B, exclusive OR B. Okay, and then you can write the sum by re-express everything in terms of P and G, so it becomes P, Ci, exclusive OR, or G plus P and Ci. Okay, nothing special here. I just basically rewrite everything in terms of the new variable G and P. That's all I do. Now I talk about adder. Do you know how to implement subtractor? Do you know about 2 complement? Okay, so if I have zero, 1, 1, 1, this equivalent to 7. How do you get minus 7? Flip everything, so it becomes 1, 0, 0, 0. Come again? Add 1. So add 1, right? So it actually becomes 1. So this is equivalent to minus 7. Right? If you sum them, this becomes 0, right? So let's see, does this become 0? 0, get in, 0, get in, 0, get in, 0. Just 9, right? Yes or no? So what is the beauty about 2 complement? For 2 complement, when you have the negative number, the sum with a positive number, the sum just works out nicely. Okay? If you don't believe me, you can perform this kind of calculation using -4 plus 3 and see what happens. But this actually tells you how you can actually implement the subtractal very easily. Suppose you have full adder. This is A0, B0. And then you have another full adder. A1, B1, another one. A2, B2, and this is CI. And if you want to do A plus B, very straightforward, right? Full adder. So you just set CI equal to 0, and then whatever that comes in, everything will do. But if you want to do C, A minus B, what do? Learn about how you convert to negative number. You invert everything first, am I right? So you have to invert all the B. So therefore, you put inverter. Right? But to change to complementary, you have to add 1, right? Do I need one more full adder? Don't need. I just have to set this guy to 1. So is how you implement the subtraction. So this guy will implement A minus B. So there is no need for you to create special function. So to implement the subtractal, you just manipulate the number by basically invert it and then send one more input to the CI to get yourself a subtractal. Okay? Now there's a reason why we want to represent the A and B in terms of G, A and B in terms of P. Okay? Let's look at 4-bit ripple carry adder. Now the name ripple carry is like ripple effect. You know what is ripple effect, right? So it basically come from one ripple to another and to another. So the problem with this kind of adder is this. All the input is available. A0, A1, B1, A2, B2, A3, B3, they are all available right at the beginning. But the result cannot be completed until the CL2 is available. Agreed? Right? Because you don't know what is CL2. So without knowing CL2, knowing A3 and B3, can you conclude SL3, S3 and CL3 confidently? Cannot. Because when this guy comes in, it will change these two results. Okay? So that's why we call it ripple, because the first one that complete is basically this guy. I get the C0 available. But only when C0 available, then I can complete this guy and make CL1 available. And once this is available, then I can get CL2 available. So you can see the ripple effect, right? So that's why we call it ripple carry adder, because we are waiting for the carry to ripple through. Okay? What is the problem with this thing?
It takes slow.
Slow. Simple, but slow. Okay? The result is not available instantaneously. Slow. So, by using the G and P, because if you think carefully, actually once you have the CI, A, and B available, all the output should be available. Everything is combinational logic. Why do I need to wait until the carry ripple through? Right? The only problem you go through that is because you don't want to figure out what is the intermediate logic. So therefore, using the P and G, we can do that. Remember, G and P, the good thing, they only depend on the input A and B. They never depend on any carry. Okay? So that's why we replace everything with G and P. Because it means once A and B are available, all the P and G are available. You don't have to wait for another carry to come through. So now we can figure out the carry. So this guy is available right away and depend on the CI. Now this guy, again, if you expand it, you see that everything depends on P and G, which means it only depends on A and B and also CI. Right? So it's also available right away. Same thing, you can expand to CL2, it becomes longer. CL3, it becomes longer. But no matter what, it tells you, once A, B, CI is available, after going through the G, after going through the P, after 1 gate delay, all the CI is available. Not all the CI. After 1 gate delay, all these individual term is available. And then you still need this OR function. So at most, you need 2 gate delay, everything is available. You get the point? Okay? So you don't have to wait for it to ripple through. Same thing for the sum. You see that all the P is available after 1 gate delay, and then followed by another gate delay for this guy. Now, of course, you have to wait for this guy. This guy requires 2 gate delay. So after this 2 gate delay, and then combine with this guy at most, after 3 gate delay, all the sum is available. Okay, so you don't have to wait for the ripple. And it doesn't matter if you have 4-bit input, 5-bit input, 6-bit input. If you construct the logic, you always can make sure the output is available after 3 gate delay, and the carry is available after 2 gate delay. Okay, so that is what we call the carry loop ahead error, because we figure out the carry in advance. So we call it carry loop ahead error. What is the problem with this carry loop ahead error? What is the problem?
We use a lot more transistors.
Yes, there is one thing, but you do see that sometimes if you keep expanding, eventually it becomes unmanageable. This guy requires how many OR gate? How many input OR gate? 1, 2, 3, 4, 5. 5 input OR gate. Right? Okay, if you keep expanding another carry, so starting from here, 1, 2, 3. Starting from here, 1, 2, 3, 4, and then 5. So if you keep adding the carry load ahead, you are going to require more and more input gate. More and more input gate, eventually it becomes not sustainable. What is the maximum input you can handle? If you try to squeeze maybe 5, maybe 6, right? But can you have 10 input? When you have so many transistors in series, it becomes no longer effective. Okay, so maybe 4 to 6 is a countable number. So this carry load again does have its limitation. It offers slightly faster compared to the ripple carry, okay, but you cannot do it forever. So then if you want to go beyond, let's say 4-bit or 6-bit, what can you do? What can you do? You can combine. You can combine ripple and carry load again. Right? You can combine carry load ahead and the ripple. So after using this guy to carry out the 4-bit quickly, the carry output sent to another 4-bit carry load ahead, and then you combine them, cascade them, you can get 12-bit, 16-bit in that manner. Okay? So now let's move on to the memory. Now we classify the memory by whether there are many ways of classifying the memory. So for example, for memory that you can read, both read and write, so we call it read-write memory. And even under the read-write memory, we can further classify them into whether it is random accessible or whether it is non-random accessible. Random accessible meaning that whichever content you want to read, say in the address, I can pick up the data right away. So random access. Now, non-random access, very simple, first in, first out. So it means the way you store the data is whatever the data available go into the memory bank, and then it just shifted like it. Therefore, the first data that coming out is also the first data that get put into the memory bank. So first in, first out. So you have no choice. If you want to read some memory, you just have to keep shifting it up until finally you get to the content that you want. For LIFO, last in, first out. So you keep throwing it, but whenever you want to read, you read the first one that get, the last one that get thrown. So last in, first out. Okay? And then shift register is the symbol. Again, you cannot randomly access. Can contain access memory. So this guy is strange. Usually it returns the memory address. So what it does is that you already know what content you're looking for. So they'll try to search through the content. Once they see the content matching what you're searching for, they'll return the memory address. Okay? So that is content accessible memory. Similarly, we also have This guy is actually volatile memory. Volatile means that once you turn off the supply, your memory is gone. Okay, it's like you guys, after the exam, your memory is gone. Okay, you retain the memory at the start of the semester. Once you turn off the semester, your memory is gone. So this guy, same thing. As long as you keep the supply, you have the memory. Once you turn it off, you don't have. The NV stands for non-volatile read-write memory. And dominantly now is basically flash. Okay, Toshiba is one of the pioneers. So I think Samsung also have it, SK Hynix also have it. There is also in the older technology, you have the so-called erasable, programmable, read-only memory. Okay, erasable, programmable, read-only memory. Now this is very useful for firmware. Okay, for firmware, especially for some electrical appliance. Now you know nowadays all the electrical appliances require some computer program, and you don't want to program it through either flash or whatever. Anyway, you know that. For example, your fridge. Okay, your fridge, you have some clock. Do what? What is the degree? How do you set all these things? The program never change. Am I right? If the program never change, I can just put all this memory. I don't have to write it. I just have to read the program. So I can put in the read-only memory. Okay? So you can put the erasable, programmable, read-only memory. Now, compared to this guy, this is electrically erasable, programmable, read-only memory. What is the difference? What is the difference? Now, this erasable, programmable, read-only memory, usually they use ultraviolet. So, very simple, you program all the chip. So now let's say you want to reprogram the chip. Before you do that, you need to erase everything, right? So how do you erase it? You just expose all the chip under the UV light. So at one go, you erase everything. So it's very efficient. Okay, very efficient. Now, electrically erasable means that you have to apply the voltage one by one so that you can erase the voltage. So therefore, this is less efficient. So still, there are some people using the erasable, programmable read-only memory. Now, flash, you already know, nowadays, everywhere, it appears everywhere. Your computer, if you're using SSD, for example, your cell phone, okay, your thumb drive, as an example. So these are all flash, okay? And there are many other candidates nowadays. I believe Dr. Lam is going to cover it. Very popular one, they call it ST-RAM, magnetic RAM, phase change RAM. Okay, these are all based on okay, before I move on. This thing is all based on electrical field. So somehow you can consider this guy as having you know transistor, right? Right? Now, if you apply positive voltage, you have a channel form, right? Right? So if you have channel form, basically it means short circuit. You know that this guy is on. Now, if you don't apply any voltage, then no channel, it's like open circuit, then you have high, right? So, for programmable memory, what you can do is, you enclose it with a metal, so this is all outside. But you cannot access this metal. But what you can do is that, if you apply high enough voltage, it's like lightning, you can somehow inject the charges into it. So by doing that, it's like, effectively, you constantly store the charges over there, and therefore, because there is a positive charges, you form a channel over here, then the whole thing becomes a memory. You store one, right? If you want to reverse it, then basically apply a negative voltage to take out the charge. Okay, something like that. So non-volatile memory. So all this memory actually depend on electrical field. But nowadays, all this memory, the new so-called new generation memory, actually depend on the so-called magnetic field. So people have find that semiconductor actually they can induce magnetic effect for the devices. and then exploit this magnetic effect and then make it a memory. So semiconductor industry is like fashion design. If you think about that, where is the very early day memory? Tape. Have you heard of the tape? Cassette. Cassette, that is actually magnetic, right? And then later people move on to CD, right? That is light, right? But hard disk is still magnetic, right? Then hard disk go into the flash is electric field. So now people go on to magnetic, right? It's like fashion design, keep flipping. So in the future, people could go back to electric field, don't know. Okay? Now the good thing about magnetic field is that they can make the memory very compact. Okay, very compact. And also the process is actually compatible to the CMOS, so you can embed the memory into the CMOS design very easily. Okay, so that is what makes it very, very attractive. One problem though, there is one problem remains to solve. Do you know what is the key challenge for magnetic? Temperature. So the magnet will lose its magnetic behavior if you heat up the magnet. You basically destroy the magnetic property. Now, for flash, right? For flash. Now your car, for example, your entertainment system in your car, they actually have this flash because they store the program. You can do the program change thing. They are using flash, right? And you know, car, if you park it during summer, very hot, high temperature, no problem. You turn on the car, it's still there, right? The program doesn't disappear. But if you switch to this guy, when you first open the car, you go in, I don't know, the temperature, I believe it is very close to 100 degrees Celsius, all right? And if everything disappears, it means every time you turn on the car, you have to reprogram, okay? Because the memory disappears. So there is still challenge. But nevertheless, for those that non-critical one, automobile actually have higher standard. So for those consumer one, I believe you wouldn't put your cell phone under the direct sun, right? You will be very protective. So for that kind of thing, probably it's really easy. Okay? And then finally, the last category, programmable read-only memory. Okay, programmable read-only memory, you cannot erase it. Once you program it, that is done. Okay, I will still cover, I don't think it's heavily used nowadays, I'll still cover it. I think the good thing about this is very easily programmable. And it's very cheap. The memory is very cheap. Everything that can be erased and rewrite again is expensive. So the key advantage for this guy is cheap. It's cheap. So let's look at how people create the memory. So for memory, you don't know what looks like a memory yet, but just remember, memory is nothing but just this guy. Because once you have back-to-back converter connection, you have one bit memory. Okay? So when I have this guy many bit, it basically just means many of this guy. Okay? So for this one, usually is good for small memory bank. Basically, your address coming from the side, raw address. So your raw address, here you have K bit. So K bit, sorry, not K bit. K bit. So for K bit, you can form these different activation. So for example, if you have 2 bit, you can activate 2. Oh, sorry. If you have 1 bit, you can activate 2. 2 bit, activate 4. If you have K bit, you can activate 2 to the power K, and that is N. Okay? So you can form the decoder logic. Basically, this decoder logic will only have one of them activated. Okay, depending on the input address. So if everything is 0, then this guy becomes high, everything else becomes low. Okay? If this is 1, let's say 0, 1, then all the rest is 0 except S1. S1 is high. So it depends on which one is high, you activate the whole row at one go. So which means you can select that particular row of memory. And then once you select that particular row, then the data will actually get transferred to the output. So it means that I can either write into that particular row or I can read from that particular row. Okay, so that is how this memory is being formed. Now it is not usable for very large memory because you think about that. If I keep designing the memory this way, if for big memory, I'm going to have an elongated shape, right? Very, very long shape. Because for this guy, at most what can you have? 64 bit. Nowadays, all the CPU based on 64 bit, right? So if you do that, maybe I have a 64 bit. In the old days, about 32 or 16, right? So here, if I do it in this way, only have the row decoder, then you will have a very long, elongated design with very narrow bit width. So if you want to handle more memory, then you have to engage both row and also column address decoder. So you split the address, make it squarish, So you split the bit equally for this guy and probably equally for this guy, something like that. There's a mistake here. This is 2 to the power k times n bit, the whole thing. So what you do is that, same thing for the row. Every time you select this row address, you make sure one of the line get activated. And one of the line get activated, it means the whole row is being chosen. But this whole row consists of n bits, but you also have 2 to the power, not k, 2 to the power k chunk over here. So basically, you are arranging the memory. Let's say 64. You have 64 here, 64 here, 64 here, 64 here, all on the same row. Okay, next to each other. Then how do I know which 64 bit I want to access? The column decoder. So this column decoder will decide, oh, you have 64 here, 64 here, 64 here, 64 here. So which 64 should I select? It depends on this column decoder. I'll select the column. Okay. So in that way, you can make the memory squarish. Okay. So it will not be elongated design. It becomes square design. And sense amplifier, we'll cover that later. Although in your thinking, memory is either 1 or 0, VDD or ground. But to be frank, when you talk about such a huge memory bank, the voltage difference is no longer VDD and ground. Usually it's very small voltage difference. Therefore, you need sense amplifier to amplify whatever the signal stored over here to determine whether it is high or low. We'll stop after we cover this one. So for this guy, if you want to have even bigger memory, then you already know how to create one block. Okay, one block. Then you can actually have another so-called block decoder. Block decoder basically determines which block do I select. Okay, so again, although I only show you the block arranged in the row manner, you can also arrange the block arranged in the vertical manner. So you can make it even bigger. Okay, so that is how you expand the memory, make it bigger and bigger. Okay? Sufficient? You want to stop here? We can continue next week. I think we have sufficient time. Or you want me to carry on? We can. I'll stop here. Any question? Any question? We'll go through the tutorial next week. So after I wrap up this lecture, I think probably less than one lecture, I think I can wrap it up. And then I'll go through the tutorial. You can take a look at the tutorial first. If you don't have time, we'll go through it. Okay? Cool. Tutorial 1 and 2. And then you guys can have a Chinese New Year.